Now, this slide simply is a review of what we said about adding vectors that are either in the same direction or in the opposite direction, which means that they either add linearly when they are in the same direction, or that they subtract from each other when they're in opposite direction. The last item I'll do first, which is two vectors at right angle to each other. This one uses the Pythagorean theorem, and we'll see that in the next slide as an example. If I have two forces, one of them acting to the easterly direction on the object with a force of 5 newtons, and I have a similar 5 Newton force acting uh, in the northerly direction, which is 90 degrees to that object, then the sum of those two forces will be found by taking the Pythagorean, calculating the length of the hypotenuse of the two sides of the right triangle. And you'll see the two sides of the right triangle in the next slide. Now, on this slide, which is a problem for you to answer as a multiple choice, let me just show you that it illustrates how to add two vectors that are perpendicular to each other, acting on the same object. So in this case, what we have is a force of 40 newtons acting to the right, a force of 30 newtons acting uh, to the north or in a northerly direction. Um, the object will assume is sitting flat on a table, and in which there is no friction of the object to resist its motion. So in this case, what we do to calculate the net force, or which is sometimes called the resultant vector, is to we draw out one of those vectors, either the one in the horizontal or the one in vertical. You can do either one first. If I draw out the arrow that is 40 newtons to the right, so on a piece of paper, if I choose to have a scale such that 10 newtons is equal to 1 inch, I draw an arrow that is 4 inches long on a piece of paper. And then I take the second arrow vector, which is 30 newtons, and place the lower end of the arrow at the tip of the first arrow. So it would be placed at the tip of the arrow that is labeled 40 newtons, and then that goes vertically up for a distance of 3 inches, where we have defined the scale to be uh, 10 newtons is represented as 1 inch on a piece of paper. So now we've got I now draw an arrow that goes from the base of the first vector, which is in this is the center of the block of the object, up to the tip of the second arrow, which in this case will be at the upper right hand corner of the rectangle that is represented by the dotted and the red vertical and horizontal lines. So that length of that vector now can be easily calculated from the Pythagorean theorem, and that's exactly what we saw in the previous slide, that if I want to find out what the length of that vector is, then I can simply take the square root of 30 squared plus 40 squared, or to say another way, I take 30 squared plus 40 squared and then the square root of that. And I get, when doing that, that the answer is 50 newtons, which will give me the magnitude of the force. And because there is more force in the horizontal than the vertical, that angle will be less than 45 degrees. Um, if they were equal in both directions, then we would have the angle of the force would be 45 degrees above the horizontal. But here it's a little bit less than that. So work the problem, and we'll resume on slide number 19. This slide illustrates how the principle of the net force acting on an object will add up to zero um, when the object is not moving. And what you see here is that the girl in the figure is supported by a rope that is both ends of which are attached to a ceiling. And there are three forces that are acting on her. One is the force of gravity, which is down, which is simply her weight, and the other is the force of the rope, which can only act along the direction of the rope because the tension in the rope defines the force. So there's a force pulling up on the right side of Nellie Newton, looking in our view, and there's a vector from the other side of the rope that is also along the direction of the rope. And these three forces must add up to zero. And what we can do, or what is shown here, is that in figure B here, we can do the vectorial addition of the two tensions in the rope, which add up to a vertical line. And the length of that vertical line, pointed upward with a dotted line, must add up to the weight of Nellie. So in that case, we now have been able to show, or that the sum of those three forces adds up to zero. So we add up first the sum of the two forces that are in the tensions of the rope, one on the right side of Nellie and one on the left. When we add those up, we get a vertical arrow that is upward, and that net upward force provided by the tensions in the two pieces of the rope must exactly balance her weight, because Nellie is not moving up or down. She is simply hanging in air. So this is a case where the object Nellie is in equilibrium and has zero force acting upon her. In this slide, a equilibrium rule can be shown as applied to an example where two painters are standing on the platform that supports them by two ropes hanging attached at each end of the platform. And the point to note here when looking at this example is that there are five forces that are that are in play here. One is the two forces of the support force of the provided by the ropes. And by the way, I should also note here that when we talk about forces, we are looking at the forces applied to an object. And in this case, the object that is for which the forces are being applied is the plank itself. So what forces are operating on the plank that the painters are on? Well, there are two upward forces that are provided by the weight, by the tension in the rope, and those two forces will be supporting the painter and the plank, and they will be pointed in upward direction. There are three forces in the downward direction. One of them is the weight of the plank, which we take to be located at the center of the plank itself, and that will be the weight of the piece of wood that the painters are standing on. And then finally, there is the weight of the individual painters themselves. And so we now have five forces that are operating on the plank. And the condition of equilibrium, in which the plank is not moving, is that the sum of those forces add up to zero. So if I choose the force on the rope as positive in the up direction, then the sum of the weight of the tension of the ropes is the sum of two positive numbers, and if I now subtract the downward forces, which is the weight of the two painters plus the weight of the plank, then that sum or difference, the sum of the two upward forces of the rope minus the sum of the downward forces due to three forces due to gravity, must add up to zero. And that is a statement that the vectorial sum of the forces adds up to zero. And this is how we explain that that the plank is not moving as the painters are doing their job on the plank. Please just answer this question and we will resume on the slide 25. Thank you. This slide also shows you how a support force can be an example of the equilibrium rule, in which the sum of the forces acting on an object add up to zero, and the object, in this case a book on a table, does not move. So in this case, the force of gravity is always equal to the weight of the book, and it will be a downward force. Assuming that the book is sitting on a table, which is not shown here, but the book is actually sitting on a table. The table provides the upward force, or the support force, which is pushing back on the book to hold it, keep it from falling. And so in this case, we know that the support force must be equal and opposite to the gravitational force. And they act on the book in opposite directions. This is also an example of Newton's third law, that for every action there is an equal and opposite reaction. That is to say that the book is applying a force on the table, and the table provides an equal and opposite force on the book, so that the net force adds up to zero. Now I'm going to let you work through the slides until we get to number 30. There will also be an example in these slides for you to work a problem, answer a multiple choice, and we'll pick up at slide number 30. Now, this slide, slide number 30, is important because it shows another example of the net forces acting on an object adding up to zero. And this is going to be the case when, in this case, the man pushing the object across the floor pushes with a force that is exactly balanced by the frictional force of the surface, the bottom surface of the box against the floor. So if we know that it takes, for example, 70 newtons to begin getting the object in motion, and that 70 newtons of force is keeping it moving at a constant speed across the floor, then the frictional force must also be 70 newtons in the opposite direction, because we know that we've observed that since the velocity of the object is not changing, then the push and the friction force must add up to zero when they are added vectorially. I'm going to let you work another problem related to this, and then pick up on slide number 35.